And now for a few handy problem-solving tips. Any real-world problem is stated as a question, and thus any real-world problem can basically be reduced to a word problem. To solve a word problem, one needs to translate the words into mathematical symbols. This is where students often have difficulties. So let's take a look at how we might translate this question into mathematical symbols. Because we are always looking at the change in some property relative to another property, we are always going to start our problem with a partial derivative. The trick is figuring out what partial derivative we want. In this problem, we want to calculate the change in entropy. And we want to do that calculation when the volume is changed. So the partial derivative that we want is the change in entropy. How does the entropy change when I change the volume? Now every partial derivative has something that's held constant, and in this case we're doing this change at constant temperature, and so this partial derivative that we want is taken at constant temperature. So we want the derivative of the thing that we want to calculate, what we want to know, with respect to the thing that is changing in our process. So the measurable quantity that is changing when we keep something constant. And that is step one in solving a problem. The second step is to find an expression for the partial derivative that expresses the question that we're trying to answer. And in particular, we want an expression for that partial derivative that has only measurable quantities in it. So we want this in terms of measurable quantities such as pressure, temperature, volume, and number of moles. So in this case, the partial derivative that expresses the question that we want to know is related through one of our Maxwell's relationships to a partial derivative of pressure with respect to temperature at constant volume. Notice that these quantities, pressure, temperature, and volume, are all measurable quantities. But so far, this expression is still in terms of a partial derivative. I can use the equation of state, so as long as I know the equation of state of my system, that is, how do pressure, temperature, and volume relate to one another? So I need to know pressure as a function of temperature, volume, and number of moles. Then I can find the derivative of that equation of state where I keep the volume constant and change the temperature. For example, if I have an ideal gas, the derivative of pressure with respect to temperature at constant volume is equal to nR divided by V. Making the substitution for the derivative of pressure with respect to temperature, we can write the derivative of entropy with respect to volume at constant temperature is equal to nR over V for an ideal gas. Once I have an expression for the derivative which expresses in mathematical terms the question that I want to answer, I simply need to do my third step, which is to separate variables and integrate. So I need to get all of my volume terms on one side, and I can write ds is equal to nR over V dV. And now I want to integrate from my initial state to my final state. And on the left-hand side, we're integrating over the entropy, so our limits have to do with the initial entropy and the final entropy. On the right-hand side, I'm integrating over volume, and so I need the initial volume and the final volume as my limits of integration, and I integrate nR over V dV. The integral of ds is simply s. I evaluate from s initial to s final, which gives me s final minus s initial, which is equal to delta s, or the change in entropy, which was what I wanted to calculate. That's equal to the integral of nR over V dV, and n and r are constant, so they come out of the integral. The integral of dV over V is the natural log of the volume, and when I evaluate that from my initial volume to my final volume, I get the natural log of V final over V initial. So to summarize, there are essentially three steps to solving any problem. Write the question as a partial derivative. 2. Find an expression for the partial derivative in terms of measurable quantities, i.e. pressure, volume, temperature, and number of moles. You often need to use the differential expression and the equation of state of the system to find that expression. Finally, separate the variables and integrate.